Today we're working on finding the real roots of polynomials. We've been working with polynomials for a few days now, and in this section it gets just a little more difficult. I'm only telling you that so you don't kick back and relax, but focus in and try to learn the material. Today we're going to identify the multiplicity of roots. There's a new vocabulary word, multiplicity. We're also going to use the rational root theorem and the irrational root theorem to solve polynomial equations, another way to solve polynomial equations. Our vocabulary word, multiplicity, it's the number of times that a number is a factor of the polynomial. So when you're solving polynomials, you're finding the roots or the zeros. Those roots or zeros could occur more than once as an actual factor of the polynomial. And the multiplicity is how many times it occurs. We'll get to that in a second. First, let's solve the polynomial equations by factoring. When we say solve, that means we're finding the roots or finding the zeros. So first I have a trinomial here, and whenever you get to a polynomial equation that's higher order, try to factor something out. Try to find a GCF that you can factor out. And here we have your GCF of 4x to the 4th. I factor that out first. I'm left with x squared, x minus 6. This trinomial can be factored if you did a, c, and b. X plus 3, x minus 2. 3 times 2 is negative 6. The difference of 3 and negative 2 is 1. Set each piece equal to 0 and solve for x. Our roots are 0, negative 3, and 2. All right, let's do another example. X fourth plus 25 equals 26x squared, standard form. Okay, it's a trinomial. It's a little strange because we have x to the 4th, x squared, and a constant. So let's try a, c, and b and see if we can figure it out. A, c, b. Negative 1, negative 25 is 25, and then you add those together to get 26. Divide by factors of a, gets everything in the right order. 1x minus 25, and this is something that's different. We started out with x to the 4th, so that means we have x squared here, and then x squared minus 1. If we FOILed this right here, we get x to the 4th minus 25x minus 25x squared minus 1x squared plus 25. So we get back to this, but it's just strange because we have x to the 4th, x squared, and a constant. So our factors are x squared minus a constant, x squared minus a constant. And don't think you're done here. You have the difference of two squares in both of those binomials, so you can factor it again. It's a good trick. Difference of squares, difference of squares. So I get x plus 5, x minus 5, x plus 1, x minus 1. Set everything equal to 0 and solve for x. X equals negative 5, x equals 5, x equals negative 1, x equals 1. So I have 4 roots. And I'm going to point out to you that our problem starts out with x to the 4th, that's our degree, and we have 4 roots as an answer. That's not a coincidence. It's very important. Another one. I have a GCF of 2x to the 4th. I'm going to factor that out first. I'm left with x squared minus 5x minus 6. A, c, and b gives me x plus 1, x minus 6. Set everything equal to 0 and solve for x. X equals 0, x equals negative 1, x equals 6. I have 3 roots. Okay? I know it's x to the 6th. That's where we're going to learn about multiplicity. Okay, some of those roots occur more than once, but we're going to get to that. Sometimes a polynomial equation has a factor that appears more than once. It's a multiple root. Example, 3x to the 5th, 5 roots, the rest of the polynomial. I factor it, my GCF comes out, I'm left with this. This is a perfect square trinomial, so I can factor it quite quickly. X plus 3 quantity squared. That's a perfect square, that's a perfect square. That is 2 times a times b. So x plus 3 quantity squared. I set everything equal to 0 and solve for x. 3x to the 3rd equals 0. x plus 3 quantity squared equals 0. Solve, I have x equals 0 3 times, x to the third 3 times. X equals negative 3 2 times, x plus 3 quantity squared 2 times. So I have multiplicities there. X equals 3 with a multiplicity of 3, and x equals negative 3 with a multiplicity of 2. That means those roots occur 3 times and 2 times. So your multiplicity of a root r, those are your roots, is the number of times that x minus r, for instance, x minus r, is a factor of the polynomial multiple times. Here's the very important part, so focus in. When a real root has even multiplicity, 2, 4, 6, 8, the graph of the polynomial touches the x-axis, but does not cross it. When it has an odd multiplicity, greater than 1, so your odd is not going to include 1, greater than 1 would be 3, 5, 7, etc. When it has an odd multiplicity greater than 1, the graph bends as it crosses the x-axis. So when it has a multiplicity of 1, it actually crosses the x-axis in a somewhat straight line. It isn't going to bend as it crosses. Let's give you an example. So this is the same polynomial as the previous slide. Okay, we factored this and got x equals 0 and x equals 3. If you remember, we had x equals 0 3 times and x equals negative 3 2 times. 2 times is an even multiplicity. So x equals negative 3 touches. It's an even multiplicity. So it gets the graph and it just touches. And then x equals 0, it bends just a little bit as it crosses. So I have a multiplicity of 2 and a multiplicity of odd but greater than 1. I can only have 5 roots, therefore 2 plus 3 is 5. So x equals negative 3 touches, so I have an even multiplicity of 2, 4, or 6. X equals 0 bends as it crosses, so I have an odd multiplicity greater than 1. So that would be 3, 5, and 7. I can only have 5 roots, so 2 plus 3 is 5. You'll get into the hang of this, and you're going to use your graphing calculator, so it'll be good. Let's try one. Example, identify the roots of each equation, state the multiplicity of each root. Standard form, so there's going to be 3 roots, because it's to the third power. Graph the polynomial on your calculator, and if you look, it bends at negative 2. So it's a bend, it's an odd multiplicity greater than 1. I can only have 3, so x equals negative 2 with a multiplicity of 3. So that root occurs 3 times. Okay, 2 more. Identify, so we're looking for 4 roots. Okay, graph it on your calculator. That's what my calculator looked like. I have a very slight bend at negative 1, 2, 3. So I have an odd multiplicity of greater than 1. And I have a straight line at x equals 1. So a straight line is always going to be a multiplicity of 1. A bend is an odd multiplicity. So I have x equals 1 with a multiplicity of 1, and x equals negative 3 with an odd multiplicity greater than 1. 3 plus 1 is 4. Double check at the end. Last example. X to the 4th, the rest of it, graph it on your calculator. Okay, I got a curve that touches at x equals 2. The touch is even. 2, 4, 6, etc. Well, I need 4. It doesn't cross anywhere else. So x equals 2 of a multiplicity of 4. We're going to continue on with the rational root theorem and the irrational root theorem next video.